All right, so today we're just gonna review your test. I don't have any set agenda, so it's really based on your questions. Let me just take 1 minute or two. I just want to confirm something. I think some of your fellow students still was emailing me about the coverage for the test. I think that one has been set very clearly on the guide, but I can confirm again. So it's gonna be basically from the beginning all the way until last Thursday. Okay, so if you look at the lecture notes, it's going to be until lecture 17, including the binary search that we did. So the makeup lecture for today, since we're doing the review session, so this one here is not going to be covered in the written test, right? But you definitely want to study for that for the exam and also for the subsequent lecture. So we also got a makeup lecture here for programming test 1 and also written test here. They are not really covered in the written test either. However, I do want to point it out, just for the stack, since in the beginning of our recursion 1 lecture, we talked about how you can trace recursive call using a last in, first out stack. So you should really know the basic manipulation for the stack, right? That's something I can say, right? Let me write it down and I'll show you why. In one of the example question there, I think that one that you have, I think 1 or 2, you have to somehow use a stack to really trace about how you can check whether parentheses are matching and also how you can do postfix calculation. I think that these two, you do need the basic operation, okay? All right, so first of all, so the up to and including March 12th lecture, which is about binary search, okay? And also we do expect the basic manipulation of a last in, first out stack, right? You can see the example questions that's available to you, okay? For example, you can look at the example questions, okay? And then the makeup lecture. Okay, so far we got 3 of them. So the one for today, which will be March 17th, and also the makeup lecture for your programming test 1, and the makeup lecture for your written test. They are not covered, okay? They are not covered for your written test, but definitely want to study them ultimately for the exam. And also, as mentioned in the guide, for assignment number 1 and assignment number 2. So these are programming assignments, but I would suggest you also go through the solutions. I might ask you something just to test your understanding. That's also set in the guide, right? Okay, may be tested for understanding. Of course, you can definitely study A1, A2. With the linked list lecture and also recursion 1 lecture, also the split array harder, right? The example we did in the class. All right, so that's something I want to clarify in the beginning. Hopefully that's clear, right? Guys, any doubts about the coverage for the test? I can clarify, right? I want to make sure you study the right amount. No more, no less. Okay. All right, apart from here, of course, in the exam question there, I can see maybe a good number of the class hasn't really tried, but it's okay. It's going to be open until Thursday morning. You definitely want to try, but the coverage here is not representative. Just some examples for what you might see in the actual test. You can go over them, and I think for many of them, they're really straightforward, very similar to what we cover in the class. And I think for some of them, you can also see some solution video walkthrough. So I think you can definitely go through the video, for example, this one here, right? Just about how you can figure out the exact primitive operation counting, right? That's something we cover in the lecture. And this example question here, you can look at the video there. You can feel free to speed it up, to save some time. But the resources is there for you, okay? So today, if I were you, I'll try to maybe go over the topics that we cover in the lecture and any part you want me to repeat or clarify. That might be the most beneficial for you because you simply don't know what's going to be on the test. Right? It's definitely going to be based on the topics we cover in the lecture. Okay. But for the example test, you can definitely take a look. All the solutions are there. You can definitely go over. Okay. All right. I'm going to pause myself here and to see if you guys got any questions. Yes?
So, regarding the question you were just on, the primitive
Right.
operations one, I was trying to do other examples, but I was not sure if my answer was correct. and I didn't know if there's an actual way of figuring out if I was correct.
Is it more about counting the primitive operations or?
Exactly.
Oh, I would say, of course, the principle would be really the same, right? Is your example very big or something small enough? Because if that's really big, it may not be everybody's interest, to really do that one from scratch in the
I
class.
think I
Yeah.
tried the selection sort one. Either
So-
selection sort or insertion sort.
Selection sort, insertion sort, right?
Yeah, I tried to find the primitive operation, but then I wasn't sure if
Okay, how about this? I can say this for sure, right? I can say focus on the complexity around the example question I gave to you, for the written test. That one day, if you can master that, and also the one we did for also the lecture, good enough for the written test. I'm not going to give you anything more complicated. I'll say insertion sort, selection sort. If you know how to approximate them to be n squared, like how we discussed in the lecture, that's good enough. Okay? But to really count the precise number of primitive operation for the complexity like a selection sort, insertion sort, you don't need it for written test. Okay? But maybe for the exam. So maybe for the exam, you can show me what you got. Maybe during the office hour, maybe we can go over it. Yeah. Okay. Yes.
Yeah, in the same primitive operations, I was going to ask, how would you go about when instead of starting at integer I is equals to 0, you start at integer I is equals to 3 or 4? What does that change in the body?
Okay, you mean about loop, right?
Yeah.
How about we do some simple example? I see what you mean. Okay, it's a good question here. Okay, good. So, okay, let me try to do something maybe simple enough. If you want it to be more complicated, we can do that. Okay, simple enough. Okay. Okay, so it's a good question actually. So let's say we're still trying to count the number of primitive operations. So what your fellow student is really asking is, what about the starting value for the loop counter is, let's say, a little bit larger. Let's say for integer, let's say I equals, did you say 3? We can make it 3, that's okay. Okay, let's say 3. And then I less than n. And then let's say I plus plus, okay. And over here, why don't we say, there might be some attribute value, okay? We just say plus plus, okay? Just that, okay? Because I believe your main question is about if we change the starting value, how is it gonna change everything, right? The main thing is, well, for this operation itself, it's not gonna change anything. It's still trying to assign some value to the variable. It's really about how many iterations there will be in total that's gonna make a difference. Okay, let's take a look, okay? So what we can do is, so first of all, for initialization stage, so this one here is just about assigning some initial value. So this one here should be counted as 1, all right? And then we ought to think about how many times this is going to be compared, and also how many times this update is going to be executed. Of course, you can think about conceptually, it would be as if we put this statement here at the end as the last statement. You can think about that way too, all right? So why don't we try to sum this up using a table, just make it more explicit for you, okay? So we can do a table here. So what I will do is, let's say we got iteration, okay? Let's exclude the initialization already. Let's say we do iteration number 1, 2, 3, 4, etc. Okay? Let's say iteration number 1, in that case, I would be equal to 3, okay? And then I less than n over here will be either true or false. And then we talk about the body of the loop, right? We can treat I plus plus as the second line in the body of the loop, right? So let's now try to work it out, okay? So we can make some assumption, right? So let's assume, let's say n should be larger than or equal to 3. Otherwise, you might just run into array index out of bound exception right away, right? Or you simply don't have an iteration. Okay. So let's say this. So let's say I value, you know what, let me just say, erase this one here. I value here will be initially 3. All right. Let's say this will be true. Okay, in which case, we're just going to compare this comparison. Okay, it's going to be 1. Okay, I'll put 1 here. And the body of the loop, since we're going to execute it, let's think about each time how many primitive operation. And this one here, guys, for this one here, how many? Plus plus. 2, right? It would be as if we said attributes equals attribute plus 1, right? If you're still not exactly feeling comfortable about plus plus, just write it out, right? Exactly 2, okay? 1 here and 1 here, all right? So here, the body of the loop is going to be 2. All right, let's do one more. Let's say we go on to iteration number 2. And of course, I would have been incremented from 3 to 4. And then let's say it is still true for now. All right. And then, of course, the comparison itself will be 1. And then since we're going to go for another iteration, so it will be just another 2 primitive operation executed, right? And so on. Okay? So we ought to think about what's really the boundary. So we're going to go with this all the way to certain iteration number, right? Yeah, go ahead. So, right. So I'm talking about in the beginning of the first iteration, I will be simply 3.
No, I'm saying the I plus plus, we put it in the body.
Do we put?
He said we put the I plus plus in the body.
In the body, yes, over here. It would be, oh, I see what you mean. Yes, I agree. Thank you so much. I completely overlook it. I agree with you. Thank you so much. And this one here will be I equals I plus 1. I agree, absolutely. So that'll be 1 and 1. Yes. And then we should say 4 and 4. Thank you. Absolutely. Thank you. Good. All right, so we know the pattern is going to be, you're going to evaluate this condition here to be true for certain times until you actually evaluate the first false, and then you exit, right? So now the question is, when will be the last value for I that's going to make it true for the last time? N minus 1, yeah, I agree. Because once you increment it from n minus 1 to n less than n will be false, right? So here, this will be n minus 1th iteration. I value will be n minus 1. And you can see that n minus 1 is still strictly less than n. So we still get true over here. And that one there is still going to take 1 primitive operation to compare. And the body here will be just 4. All right? And at the end of the n minus 1th iteration, and as we're going to, let me use a different color, right? There will be no nth iteration because we would have incremented from n minus 1 to n. And here, n less than n is going to give us false. But that particular comparison will still count as 1. But we're not going to go for any more iterations. Any doubts so far? We're good? All right, so now let's sum up. All right, so basically we're going to sum up. First of all, we got this initialization, don't forget. Okay, it's going to be 1. This will be the init. Only executed once to initialize the loop counter. And then I'm going to say plus. Let's now get this one here. Okay. For this part here, every time we check the condition, it's going to be exactly 1. How many times do we check it? N times, right? N times, right? So there will be n minus 1 times it's going to be true. And then the last time is going to be 1. Okay, already there. Here. So it's going to be basically n minus 1 plus 1. Okay. So n minus 1 here is about the I less than n evaluate to true. And the last time over here is going to be the I less than n evaluate to false. All right. And let's also try to count for the body part. Each time when you execute the body of the loop, it's going to be 4 primitive operations. But exactly how many times? N minus 1, agree? It will be whenever the I less than n is going to be true, then we have to execute the body of the loop for one more time. So the only time we don't really go ahead is when this evaluates to false already. Okay? So it's going to be 4 times, okay, plus 4 times n minus 1. So think about n minus 1 here is about the I less than n evaluate to true. And 4 here is what we just calculated right here, right? About this one here and this one here. Okay. You just gotta simplify that, right? And I'm pretty sure you can do the simplification. Okay, that part I can leave it to you. Does that answer your question?
I didn't understand how if we're studying I starts at 3, would it change the number of iterations to like n minus 3?
Right. You will actually. Maybe there's something. Okay, you're making a very good point over here. Okay, so I think here. Okay, I see. Again, very good, right? Guys, I'm thinking on my feet, so I may not be as perfect as you are, right? So I think you're failed to make a very good point. How many rows do we have right here? All right, very good. So in order to know it, I'm gonna modify. I like this one here. All right, first of all, let's think about the value here. Now I see exactly what you mean. The number of rows we have over here, is about how many numbers we have between 3 and n. All right, which will be the n minus the beginning plus 1, which will be n minus 2. So that means we are going to evaluate this condition here n minus 2 times. Guys, agree? Let me say that again, okay? I want to make sure, okay? What I did wrong before was I simply used n minus 1. N minus 1 is simply just the iteration, right? So this one here is not exactly right. This one here should be n minus 3 and then n minus 2. However, I would say for these two, you can look at that maybe at the end. The critical part is really about when you look at this row over here, this column here. Really asking about when the value of I is going to go from 3 all the way to n. How many times do I really go do I need to increment I from 3 to n? You basically calculate what's the size of this interval. And we talk about how you can calculate the size of the interval. N minus the beginning and then plus 1. So that's why we got n minus 2. Are you okay with this? Okay, good. Okay. So let's change our answer accordingly. Okay, I'm gonna use a red pen to tell you. Okay, this part here stay the same. Okay, and overall here is going to be n minus 2. Okay, but we know that one time is going to be when you evaluate to false. So that means this part here is going to be n minus 3. Okay, and then this part over here is going to be just about when you evaluate to false, which will be n minus 3. So this part over here, okay, let me just break it down a little bit more, right? Just about this part. Only this part, okay? This part here is about the number of times I less than n evaluate to true. We're going from 3 all the way to n minus 1. 3 to n minus 1. And the size will be n minus 1 minus 3 plus 1, right? And minus beginning plus 1. So that'd be n minus 3, right? Which is what I got over here. Okay. Guys, are you okay with this? Or any part that you need further clarification? Go ahead.
When you're calculating number of primitive operations, say there was like an if statement.
Sure.
You normally count for worst case scenario.
You count for words, yeah. So that's good. So I think I kind of mentioned that maybe just one sentence in the lecture. When you only when you're accounting for a primitive operation, you don't consider the logic of the program. Just think about the if statement is going to be executed for every time.
Okay.
Yeah. Yes.
Is the plus one necessary for the middle of the sum? Because n minus 2 includes the false evaluation.
Right. That's true. That's true. I think I do apologize for a little bit being messy, but I think to really see the whole thing about how I did it wrong and how to correct it is actually valuable. Okay. So just for this part, let me be very clear. Okay. Let's say just for this part. Okay. Let me be very clear over here. So overall, it should be n minus 2. Okay. However, we can break it down into two parts. We got evaluate to true. That would be n minus 3, which is how I calculate it over here. Okay. And also evaluate to false will be just 1. So if you add these two up, it's going to be n minus 2. Yeah, that's how you see that. Good. I think this one is good. I really like the question that you asked, how we're able to, to see exactly how things should be changed accordingly. Yeah. So even if this one doesn't really appear, because I cannot change the test anymore, it's already there. I'm not gonna add this one if that's not already there, right? Just in case you don't really see something as complicated, maybe or similar to in the written test, watch out for the exam. All right. Yeah, because I think these kind of concepts are really important for you to count, right? But I would say the tip would be, the number one tip, whenever you want to calculate a number primitive operation for the loops, watch out for initialization, and also watch out for how many times you're going to evaluate the Boolean condition to be true, and plus 1 time that's going to be false. Accordingly, what will be for every iteration, how many primitive operation will be there. So that's going to be the basis for you to multiply by number of iterations. Okay. Any follow-up to this? Okay, good. Okay, next one. Yes.
I don't think is it reasonable to ask a question?
Uh-huh.
It's not I equals to 3, it's I equals to j, and then count the primitive operation.
Sorry, say it again. You want to change it?
Yeah, if we had a double for loop and it was like
It's definitely possible. Yeah, it's possible.
next one is j.
So yes, you say that you want to have 4 and then maybe integer, let's say j equals I.
Yeah.
Okay, sure. It's definitely possible. So I would say for this one here, we did one example about triangular sum, something like that in the lecture. And also there's something very similar in the example test as well. Maybe try to focus on those. Yeah, I'm not going to give you anything more complicated than that. So your fellow student question was, this is all good, but what if I want to add another nested loop right here to say the loop counter j and the starting value is I. It looks to me it's going to be more like a triangular sum kind of question. So that one here, you can just review the lecture slides and then try to see how you can go from there. Right. I'm not going to give you like a triple nested loop. How about that? I can tell you, no. Okay, I think double nested is realistic for this course. Okay. Yeah, just say one more tip. Just say in general, if you're given some iterative algorithm, like either single loop, double nested loop, either to approximate or to count the primitive operation, the best way to go for that is to have a table to really see what's the pattern for the loop counter. And also what's the pattern for this condition deciding when we should really exit from the loop. That's really what you should really do first. Once you observe the pattern, you will be able to sum up. Sometimes you may have to apply the formula for arithmetic sequence sum, which is not the case here because I think it's rather simple for the pattern. But maybe for the nested loop, you have to. All right, next question. Yeah, maybe before, I would say before Thursday's test, you definitely want to maybe redo at least the exercises we did in the class about counting. and also approximating, right? We did quite a bit of examples in the lecture. Okay. Yes?
Can you re-explain arithmetic sequence?
Arithmetic sequence sum? Sure, I can. Let me not worry too much about the derivation part. I'll just tell you the facts that you should know. If you want to see more details, you can refer to that part for the lecture. Let me make sure. You talk about arithmetic, not geometric, right? Okay. That one's even simpler. Okay. Arithmetic in general, for example, I might have, let's say, 2 plus 4 plus 6 plus 8 plus something, maybe all the way to, let's say, I don't know, 10, 24, right? Why is this arithmetic? Because you have some initial term, that's good, and between every adjacent term, you have some common difference, plus 2, and then plus 2, and then plus 2, right? And if I have this, the formula is beginning plus the end multiplied by k, which will be the number of terms, divided by 2. Right? Now the question is, what's k? Typically, I would say maybe the number of terms in the case of arithmetic sequence or geometric sequence might be the trickiest to figure out, but it's not too bad. The tip will be you want to look at the pattern for the individual number, right? So here you can see that they happen to be multiple of 2, right? So I can just go for, let's say, for example, this will be 2 multiplied by 1, okay? And this one here is 2 multiplied by 2. And the third one, 2 multiplied by 3. And this one, 2 multiplied by 4. And I'm pretty sure you know this one, 2 multiplied by 512. So now we are basically, well, the 2 here is common, fixed. So what we should really look at to really figure out a pattern is 1, 2, 3, 4, all the way to 512. So we are really trying, k will be the interval between 1 and 512. Right? This one here, well, if you want to apply a formula, but it's 512, but I can apply a formula. The end minus the beginning plus 1. So replace that by 512. Right? You calculate it. Okay, does that answer your question? Yeah. Of course, this is just one example for the arithmetic sequence, right? Sometimes it could be that maybe the end may not be like a concrete number. It could be 2n or 2n plus 1. You know, you just got to calculate accordingly, right? Mm-hmm. Maybe take a look at a triangular sum or similar example. We do talk about how you can figure out the terms over there, right? Good. Are you guys comfortable with the tree traversal in general? Okay, yeah. Yes, please.
Are we able to go for one of the practice questions that was posted on eClass or not?
Yeah, you can. Just tell me which one. I can give you some highlights because if that one involves maybe some solution walkthrough, maybe I can refer you to the video. But I can tell me which one are you talking about.
It was about counting primitive operations. I think it was question number 5.
Question number 5 over here. Yeah, I think that one there, I can maybe talk maybe just in general how you should really go about it. But I think for the exact calculation, maybe you can also refer to the video. Okay, I can talk about it since you ask. I don't want to simply completely not discuss it. Okay, let me try. Okay, a bit. Okay, give me just one moment. Hopefully this will work. Okay, good. All right. So, oh, I'm so sorry. There we go. All right, right here. Okay. All right, contains duplicate. Okay. So, okay. I think it's a good question here. So let's give it a try. So you can see that we basically got a nested loop. So there's an outer loop right here. And then we got inner loop right here. Okay, let's just highlight it. Okay. And then we got if statement, but as your fellow student asked, so I said to really count, you don't have to worry about exactly which iteration might execute the body of the iteration, the body of the if statement. Just assume, in the worst case, all the lines are going to be executed for every iteration. That's okay. We make that assumption, right? So basically, think about indentation here also suggests this part here. Let me say this is 1, and also the I++. Okay, let me say this is star. This is star star. Just to start with, star here. So here, line number 7 executed depending on the number of iterations of the outer loop. Would you agree with this one here? Good. Okay, similarly, just write down the idea. Okay, this one here, star star. This will be depending on the inner loop. Line number 4 to line number 6 will be executed depending on the number of iterations of the inner loop. Okay, so what I can ask you to try is to, first of all, if you calculate just about this block over here, how many primitive operation, right? Array, you can see, let's say, comparison, logical, array indexing, and also comparison. Also return, and also this will be 2, right? Adding up together is about each time is going to take that many operations. Okay, I'll let you calculate that, right? It's also, you can also look at the solution. Okay, so this one here, how many? Okay, and then we know that this one pretty well, just from before, is going to be 2. And line number A here, just stand by itself, is going to be just 1. Okay, so now what remains is to look at the pattern, right, for the I and j, right? It's very similar to the triangular sum. Let's do a little bit. Okay, so we're going to look at the pattern for, first of all, for the outer loop. So we start with 0. The I value here is going to be 0, 1, 2, all the way to, right? So what will be the last iteration value for I? I agree, exactly, right? Okay, n-1, and then of course let's still put n here because that one will still trigger some calculation, right? It will still trigger the comparison of this Boolean operation, which will evaluate to false. Okay, I'm just write it down. You can think about this part here is going to be the true value, and this part over here is going to be the false value. Okay, so that means accordingly the number of the iteration will be from 0 to n-1, right? That one there will just be n iterations. So that's all good? Okay, good. Okay, let's look at the second dimension, right? And the j value there, let me see if I can change this one here. Okay, that one there. So the j value is going to be, okay, from 0 all the way to, again, n. Of course, you guys can try maybe some variants, maybe you form the group and then try to change. For example, you may want to say, rather than 0, it could be 3, or it could be maybe I, as you said earlier, right? It's just that this one here is not going to be triangular shape, okay? It may be more like a rectangular. So j is going to be from 0, 1, 2, all the way to, again, n-1. So these would be the true value until we get to n. So that would be the false value. Okay, like that. Okay. It's going to be very similar for every iteration, right? So we also got 0, 1, 2, all the way to n minus 1, and also we got n, and etc. Okay, so where would be the very last j value that we're going to have? Oh, sorry. So here, it doesn't really depend on the I value. So we're going to go all the way to here as well. Okay. And also we got 0, and then 1 and 2, all the way to n minus 1, and then n. All right. All right, so far so good. So this is what you should do. Okay, I'll give you the idea. First of all, let's look at just this part. This part over here is about how many iterations we're going to have for the inner loop, right? From 0 to n minus 1. We know that it's n. Okay? And also from 0 to n minus 1 here is also n. Is also n. So n times n is going to give us n squared. So n squared over here is about the number of iterations, number of times you're going to execute the body of the inner loop right here. Right? Because we know that for every combination of I and j, it's going to correspond to one execution of from line number 4 to line number 6. All right? So n squared over here, you're going to multiply by this answer over here. The number of primitive operations from line number 4 to line number 6. Okay, this will be one part. Okay, and this part over here, let's see, this part here. Okay, this part here is just about comparing j less than n, right? So those are the values. You want to actually make sure that each one of them will be just 1. So this is about the number of times j less than n evaluate to false. Each time evaluate to false is going to be one comparison. And then how many times? 1, 2, all the way to here. So from 0 all the way to n minus 1. You got to evaluate this many times. Okay? 1 multiplied by n. Okay? Okay, here's another one. And then also we got this one here. You only evaluate this condition here, I less than n. Okay, this one here, the number of times I less than n evaluate to false. That one there only one time. Right? Because once you exit from the outer loop, you're done. Right? Okay. So basically you add them up together. You're going to basically add up this part here, and also this part here. And finally, make sure you also add up to here as well. Add them up together, you get a final result. Of course, in the written test, it's very likely I might either give you some multiple choice, you can get a select answer. Let's say in the exam, it's more likely I might just want to see your work of deriving the primitive operation. In that case, even if you got maybe the result not exactly correct, you might still get some partial marks. But that's more the context for the exam. Okay. Yeah.
So for the written test, do we get the same amount of time as process?
Yeah, it'll be 1 hour. Yeah, the reason that we couldn't really get you 80 minutes is also depending on the availability for the lab. Since we don't really have a scheduled lab or tutorial session for this course, I had to somehow secure Williams Small Center, and we do have another, like something else going on. Yeah, so yeah, about 1 hour. I do know how much time you have. Yeah. Guys, any question about trees in general? Real good? Yeah, I know. Historically, I know your fellow student from the previous 10, they're also a little bit struggling with counting. I think, yeah, it makes sense because you got to be very systematic and very precise. It is a challenge. I think it's good for you to tackle that. Okay, let me just pause the recording. Yes, please.
For the binary tree properties, like, how are we supposed to generally use them? Like, are we going to be asked to like derive them, or is it just like?
Oh, you mean for the properties, right?
Yeah.
Okay, good. Okay, in general. Okay, that's the one you're talking about, right? Okay, sure. I know what you're asking. Okay. I think your fellow student was asking about, for binary tree, we have the properties that we derive together. You know, for example, right? I think we did 6 of them. I would say, I'll tell you 2 things, okay? Number 1, I think it's really important for you to understand about the shape of the tree for the minimum case and the maximum case. So that just in case you forget about the number, you just cannot recall exactly, you can still derive them yourself. For example, let's say, if I want to know what will be the minimum case for internal nodes, I know that minimum case should be when I got a slanted tree, slanted only one way. In that way, I know that the height is actually h, so to really see how many nodes I have, it'll be h minus 1, for example, right? That'll be, so point number 1, you want to understand about how we derive each case, that's for sure, right? In the written test, maybe I'll just give you multiple choice about how many you have. I might say, okay, let's say the height is 3, and then what will be the minimum number of internal nodes? In that case, you have to tell me it's actually 3, for example. Another point number 2, if I were you to take the test, I might just want to save some time for my test. I might just memorize the properties. I want to be 100% honest. However, given the nerve and also the time constraint in the test, it's very likely, sometimes you might be thinking, oh, should it be h or h minus 1? It's possible, right? In that case, I think that's why you also want to know how to derive each case. Look at the tree shape and see how you can derive accordingly. I think both are important, right? Mm-hmm. Does that kind of answer your question? Yeah, yeah. Yeah, I think this one here definitely is very useful, right? I think 2 to the k minus 1. Right? But just in case you forgot about, oh, should it be 2 to the k plus 1 or should it be 2 to the k minus 1? Just in case you forgot, you can still go back to that page and try to derive that quickly. I also take this opportunity to really also get prepared for your exam halfway because the coverage overlaps, right? Although our exam is pretty late in the exam period, but I think it's good. They're going to try to study this part of the material because once we resume the class next Tuesday, things will get, just a little bit more advanced, right? We're just trying to build up the material. For example, complete binary tree, right? Make sure you review the definitions, make sure you know how to define them, right? I'm not suggesting that might be on the test, I'm just saying that's something you should know. It's good material for you to learn, right? Know the difference between complete binary tree and also full binary tree, okay? And then also the page I was referring to is right here. Okay, let me show you. Oh, right here, right? Just about how you can calculate the maximum number of nodes in the binary tree, depending on how many levels you have. I think this page is very important too. And just about geometric sequence sum. Again, two choices. Number one, you should really know the derivation process. But number two, I might just memorize the formula. Okay. Just in case you forgot about precisely what it should be, you can still derive it yourself quickly. Okay. All right. Let me see if there's anything else. I think you guys should make sure you also understand. For example, table here, right? It's just comparing about array, singly linked list, and also doubly linked list. You should really look at the running time and see why they might be different in some cases, right? Yeah, stuff like that, right? As you go over the slides and iPad notes, you should always ask yourself why things are that way, or why things are not the other way. Yes?
Can you go over asymptotic notation? Like, how would we see a question on the written test about asymptotic notation?
Asymptotic, you mean like a proving or?
Yeah, like upper bounds. Like, would we be asked, like, what's C, what's N0?
Sure. Let's say, are you referring to something like this? Okay, sure. Okay, maybe rather than creating something from scratch, since we've gone over so many examples, let's take a look. I'll give you the highlight, right? So I think that this kind of question there is more like a mathematical question. It's not like a given a Java code, you're going to figure out running time, right? That's something we just did. So this will be if you're given some function here, and then you want to, maybe it wouldn't even give this to you. I want to ask you, part one, number one, what's the asymptotic upper bound? You can simply choose the highest power. That'll be n to the power 4. All right, that's number one. Number two, once we decide it should be n to the power of 4, so now we should really prove about it, right? So to prove about it, I will highly suggest you guys try to revisit this diagram over here, right? So that's about the f of n and g of n. So f of n is the running time function you're given. And the g of n here is the reference function. So somehow n here is not yet upper bounding the runtime function. It's actually after we have changed the slope of the g of n. For example, if I simply multiply the g of n by 9, by some constant factor, it's going to make the slope of g of n steeper, right? So in that way, we know that starting from a certain point, so we call this n0. Starting from n0 over here, and we call this the c constant, right? After changing the slope for the reference function, starting from n0, we can see the g of n will be larger than or equal to the f of n, right? So that's really the big picture you want to keep in mind. So how do you find it? So for running time function involving only polynomial, which will be n to the power of something, you will always be safe. You simply just choose the highest power, in this case d, and then you try to choose the c by adding up the absolute value for all the multiplicative constant. And then n0 here guaranteed to be just 1. However, things might be a little bit different if you involve, let's say, log. In that case, you can still apply this formula here. You can still try to choose the c this way, but for n0 here, maybe 1 or maybe something else. So that's why in the exercise, it will always ask you to verify if the upper bound effect is going to happen at exactly 1. If it is not, you may have to try maybe 2 and then 3. Normally, it wouldn't take that many more try. Okay. Okay, let me go back to here, right here. Right. So this is the highest power, and then we choose the c, which would be the sum of the absolute value, right? Especially when you got minus 3 over here, make sure to take the absolute value. Okay. And then n0 will just be 1. Okay. So in this case, because there's no involvement of the log, so you can simply just say n0 equals 1. I would say if you really got some time pressure, I think in this case, you don't need to double check, like a verify. But I think if you see any log as part of the running time, you definitely have to verify because n0 may not be 1 in some cases. Okay. Does that answer your question? Okay, good. Yeah, but in case you're going to take a 3101 again with me, maybe at some point later, I think for your other professor as well, I think the emphasis will be similar. We wouldn't emphasize so much on proving this kind of runtime function mathematically in 3101. Instead, we're going to emphasize more about given the algorithm, either as a bullet point like intuition, like a description like of the steps, or maybe given Java code, pseudocode, how can you transform, how you can derive the approximate running time from the algorithm. It's going to be more of the emphasis in 3101. But this one here just foundation at this level. So do expect a question like this in the written test and exam. Okay. But once you get promoted to 3101 later, you just have to make sure this one is something you can do on a sketch paper. Okay. Well, since we talk about running time, so I think it's also useful for you to know conceptually. Okay, let me show you here about the properties. Right, we talk about, for example, proper subset over here, and also about the different families of the function. Right, maybe just make sure review the properties. They will definitely be useful not just for the test but also for the exam as well. And then about, so all the property here, okay? So it seems to me you guys are rather comfortable with trees in general, because I can see, similar to your fellow student from the previous year, usually when I held a review session, question mostly about asymptotic upper bounds, yeah, which is okay, right? Nothing wrong with it. Yes?
Can you go over maybe more challenging tree question? Because the written test had a fairly basic one, the example.
Yeah, because when you say more challenging, right, then I'm going to make up on my own right here. Let's see. What did you have? Last question. Sure. Okay, choose the descendants. Okay, how about this? Yeah, we can do this together. Not necessarily much more challenging, but I want to give you some idea, right? Let me first of all just go back to where we were, right here. And then that one is just about ancestor, about descendants. So I'm pretty sure you know how to calculate ancestor. Okay. Yeah, one moment. It's just pasting. Good. Okay, let's say here, first of all, the number of subtrees. How many? I think we did this one, but I'll just start with this. How many subtrees? Yeah, corresponding number of nodes, because each node can be the root of the subtree, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? Not necessarily more challenging, but a variant of this question. Let's say the number of subtrees of sizes between 3 and 5. Could be 0. I just made up the number actually, but you see the idea, right? So here. So that means, okay, how do we solve this, right? I can adjust it later, okay? So that means you're gonna find out how many subtrees we have of sizes 3 or 4 or 5. All right. So now let's take a look. Okay. So the alpha here is good because the subtree size is 4. We agree? Okay. And then so for now for Anna and 4 and then I think that's it. Right? Okay, good. That's fine. Only one. But it can adjust the number. So that will kind of force you to really identify only certain subtrees. Okay? And let's see here. Another one, for example, let's say, given a binary tree of height 7. What's the maximum number of nodes? It's not to do with the family tree, right? But I'm giving you a concrete height. So we have to recall that formula, right? It should be 2 to the power of something here, and then minus 1, right? So now here, that should be k. Okay, you can double check. I believe it's h plus 1. Simply because, if you think about it, so here, so we got level 0, level 1, all the way to level 7, right? So we basically add up a geometric sequence. So level 0, level 1, all the way to level 7. How many levels do we have? 7 plus 1, because we start from level 0, right? From 0 all the way to 7, right? So that should be 7 plus 1. And this one here, you should be able to calculate, right? So what's 2 to the 8? Well, you can double check, okay? That's fine. I believe 256, I believe. Okay, minus 1. Oh, by the way, 2 to the 8 will be just 2 to the 4 multiplied by 2 to the 4. 16 multiplied by 16. You can do that quickly on paper too, right? There'll be no calculator allowed. However, any numbers I give to you will be small enough. You can calculate on the paper. I'm not going to give you, I want you to calculate 2 to the power of 24. It's not like that, right? Don't worry. Something you can definitely calculate on the paper. Okay. That's just an idea about more advanced, right? Also, you can think about if I give you maybe a tree, and I want you to do maybe pre-order traversal, and also post-order traversal, right? That's also possible, right? And also, I can ask you about the definition, maybe for what does it really mean a tree is actually full, and what does it really mean when a tree is proper, right? Yeah, that's also possible. Guys, any other questions? We still have time. But if you want to leave earlier, that's no problem, right? We'll wait a bit, yeah. Let me see. While you're thinking, shoot me the question whenever you're ready. But meanwhile, let me see if I got anything else. I can, again, I'm not suggesting what might be on the test, but I think that's something you definitely should know, right? Important for this course. Oh, question, right? Yeah, sure. Okay. Go ahead, please.
I don't know if you speak too long, but I just wanted to understand if you could explain your intuition for assignment 1, the recursive, the last question with the steps.
Oh, that one might take a little longer, I think, for the steps.
Yeah, just kind of like how you would go about tackling it, not necessarily code.
I can download the code, and then we can take a look at very quickly. Okay, it's possible. Yeah, since you asked, I think I should really respond to it. Okay, 2101, assignment 1, right?
Yeah.
Okay. So what we can do is go to assignment number 1, solution code, right? And you said the last method, task number 4. Okay, good. Okay. How about this? Okay, this one, let me see if I should be able to, let's say, copy this one here. We may not go for 100% DR. Maybe I'll give you some, you said just intuition, right? Okay, we can do it. Okay. Okay, let's see if it might work this time. Let me try one more time. Yeah, if it doesn't work, I can just use the mouse. Give me one moment. Okay, let me try one more time. Sometimes it works, sometimes it doesn't. Okay. Okay, that's good. Okay. The code is here. Okay. I think the most important thing here is to see the pattern we're doing. Okay. So that's assignment number 1, solution, right? You do have access to it. So here we got task number 4. So that's a public version of the method, right? And what we're doing is we're creating a private recursive helper, climb stair strategies helper, okay, right here. You can, let's see where we are calling it. So we are only calling that right here, helper, okay, right here, okay. I think the most important intuition is you can think about these two. Okay, so this is the solution set, and this is the solution so far. So you should really think about these two are the sets that are accumulated between recursive call. But ultimately, we're going to return the value for this one here. This one here is more like an intermediate value for you to compare. Okay, so you can see we got solution set and also current solution. So whenever you're passing these two, we're passing the same variable. We're not really creating new objects, really. Okay, it's more about we're using call by value. Okay. However, the only but the difference between these two is like this. Okay, you can think about the current solution over here. Over here, you can think about before making a new recursive call. Take one step for later to assume. So what I meant was, let's say in general, if you actually start from here, let's say this is my current recursive call, right? I might either go for this way here, I might also go for this way here. So going to the left, for example here, might result in some current solution that's different from if I go to the right. It's like a split array. You might decide to either put the element in group number 1 or group number 2, right? So that's something you have to create some intermediate solution to pass to the recursive call, right? Yeah. That's what I can think about to give you some intuition. Of course, also there's some specifics about how we do the steps, which will be specific for this question here, right? Yeah. In the written test, as I said, it's not really a programming test. It will be, I wouldn't really just ask you to write code from scratch, not really. So I would say try to understand exactly how things will work, and then I might just ask you maybe multiple choice, just about how things should be perceived, things like that. Yeah. Sorry, can you repeat again? I just cannot hear you clearly.
Are there going to be any problems on trees that are
Well, it's a written test. Of course, primarily it will be more about understanding. But I would say there might be some short question there where you might be asked to write some short fragment of code. It's possible. But not to the extent that you have to do for a programming test. You wouldn't be asked to really program a method just from scratch. No. But I think for the written test, if you just go over maybe the code fragment we did in the class, I think that should be sufficient. Now, of course, look at A1 and A2 as well. You don't need to look at A3. Yeah. Okay, we still got about 10 minutes. You guys can keep shooting to me questions. But meanwhile, okay, let me see if there's anything else. For example, tracing, right? So if you're given maybe the method that we discussed in the class, how would you do tracing, right? So binary search could be one example. I think we did so many tracing exercises, in the lecture. So maybe look at the tracing as well, okay? And then, of course, hopefully you're comfortable doing this, okay? Pre-order, in order, and post-order, okay? And then, let me see anything else. Okay, also the basic definitions for all the terms about parent, root, children, siblings, descendants, ancestor, right? Things like that. Okay. Also, what's the definition for depth and what's the definition for heights? Right? It should also be clear about these definitions. Okay. And we only started talking about just how you can solve the recurrence relation. Of course, that's the only one we did. So if I do ask you anything about solving recurrence relation, it would not be more complicated than this. But I would say it's good for you to study at least this example here for this coming written test. And later on for your exam, you have to make sure you also try to study through the solving the recurrence relation for merge sort. That one's going to be more complicated, right? But the makeup lecture is already there. You can look at that maybe after the written test, before next Tuesday. Okay. Okay, let me see if there's anything else. Yeah, mathematical induction, make sure you know what the steps are, right, in general. And that's about bounding the number of nodes, etc., about the math properties, okay? Okay. I think that this one here is a nice summary, right, for you to use it as a guidance about the properties we spoke about. All right, and then, yeah, this one here, again, this was really important. I think a short fragment like this, right, how you can define the depth and how you can define the heights, I think that's something I might ask you about too, right, in the test. These are very short methods, okay? Okay, order versus unordered tree, right? Know the difference. And then terminology, right? Yeah, I think that knowing exact difference between depth and heights is definitely very fundamental, for sure. Okay. Okay. Yeah, subtrees, we just spoke about it, right? What's a smaller subtree, what's a larger subtree, and if I give you certain size range, how can you figure out the range? Linear versus nonlinear, right? I think this table here is rather thorough about the different kinds. Okay. Okay, let's see. If you do have any question, please shoot me out. I'm just talking, right? So you can let me know. This table here, definitely important, okay? I believe there's some question there in the example, just about given maybe the programming assignment, how can I rearrange their order so they will work? That's also possible, right? You can look at some example, okay? I think my tip would be if you're given any coding question, like moving around a sequence for linked list, the best way to do it would be, first of all, visualize all the nodes involved so you can see how to set the pointers and the references. That'll be the number one tip I would give. That's how I would do it as well, okay? Okay, insert between, and also, yeah, why do we have doubly linked node as opposed to singly linked node, right? Know exactly why each attribute that we're introducing, why are they the case? Okay. Also very important, right? If you simply move from singly linked list to doubly linked list, you want to know why we're doing it, right? Not necessarily just for performance, might be for something else. Okay, and then, okay, that's just a subtable about array and singly linked list. Yeah, there are many stuff that we talk about, so I just want to see if there's anything in particular, if you want to do some last minute review. And about the general steps, right? If I give you some new operation to implement for the linked list, you ought to know what should be the separate individual step you should really apply, to the operation, okay? Okay, trading space for time is also a very important idea. And then, okay, constructing nodes, right, etc. Right. I think this one here, even though it's only about drawing, I think that this page here is also very nice for us to really summarize visually about the different kinds of operation you can do on the singly linked list, like inserting and removing either to the beginning, to the middle, or to the end. I think that this page here is also very nice for you to review. Okay. Right, insertion sort, selection sort, right? Just some exercise that we did earlier. Okay. All right. Yeah, and then we kind of back to sorting. Okay, the different sorting orders, right? That's also very important to know. And also inserting into the array why it is linear, right, as opposed to constant time. And arithmetic sequence, right? Something you just ask. Okay. Okay, triangular sum. I think this one is very important, right? So here you can see the value of j will start from I as opposed to some constant. So that's why you got a triangular shape right here. Okay? But the principle will be very similar. You want to identify the pattern for I and j and then try to see how you can count accordingly. Okay? Yeah, and then we're back to the asymptotic lecture, right? Over here. Okay, very quick, walkthrough. I think we cover many stuff. I think it's a very good opportunity for you to review the stuff, right? It's not only just for the test, also want to make sure you're prepared for the next course too, 3101. Any questions? We still got 3 minutes. I'll try to post the video maybe tonight. I'll try. And then if you still want to review, you can do it. Yes, please.
If we have time, can we briefly go over postfix operations?
You want the prefix and postfix? It's just an example or?
Yeah, there was one specific example in the practice.
Sure.
Where I think it was 3, 4, 5 star minus, and the answer ended up being minus 17, but I couldn't quite figure out why.
Sure. About example question, right?
Yeah.
Sure. Let me we can do that one. Yeah. Yeah, for that one there, you also got some solution video you can look at. Can you tell me exactly what it is?
Yeah. The numbers were 3, 4, and 5, and they were followed by star and minus.
Okay, good. So the way to trace it, if I remember correctly, right? So whenever you see you're going to use a stack. So this will be the only part I will expect you to do on a stack, just push and pop, okay? So whenever you see a number, you're going to say 3 here, and then 4 here, and then 5 here, all right? And then when you see an operator, that means you're going to pop, well, it's a binary operator, so I'm going to pop 2 numbers from the stack. So I'm going to pop 5 and also 4. Okay, so multiply them. Okay, so that one there is going to be 20. So that means after popping them off, I calculated some number which will be 20. Okay, over here. Okay, and then we're going to look at the next number, well, next element, which would be minus over here. So that one there is going to, we're going to pop again, 20 and also 3. Okay, and then apply the minus is going to be 17. Is that the answer?
The answer was minus 17.
Minus 17. Okay, yeah. I just forgot the specifics, but I believe this particular order. Let's be precise. So here, when you pop, okay, at this point here, so here we got 20 and 3. So when we first of all say pop, it's going to give you 20, and when you pop again, it's going to be 3. Okay, I believe the assumption is the first one that's going to be pop is going to be the right-hand side, and this one here is going to be the left-hand side. Okay, so that means we got 3 here and we got 20 here, and apply the operator is going to be minus 17.
That makes sense. So you're just, the idea is that you're putting the, like basically onto the stack, you're putting the, whatever you get from the first operation back onto the stack, and then when you have another operand, you pop it again.
That's correct. That's correct. I think the main specifics you got to remember, which is consistent with what we said in the solution there, is the let's say sometimes the operator maybe that doesn't really matter the order, but I think it's good to stick to the order. So especially for minus, if you say x minus y, it might be just different from y minus x. So the very first one that's pop up, okay, let me finish this. The first one that's going to be pop is going to be the right operand, and the second one is going to be the left operand, and then do the minus. Okay. Yeah. All right, guys, any other questions? We all good? Okay. Good luck, and then I would say study as much as you can, and then I'll see you on Thursday. Okay, take care.